Assalamualaikum and good evening. My name is Rujita Binti Abdul Samad. I'm going to present about my project and presentation of photodetector. This is the journalist. The first one is high performance photodetector based on an interface engineering assisted graphene silicon Schottky junction. The second one is ultra fast photodetector by integrating perovskite directly on silicon wafer. And the third one is light intensity dependent photoresponse time of organic photodetectors and its molecular origin. This is the journal one, which is about high performance photodetector based on an interface engineering assisted graphene silicon Schottky junction. The executive summary. The problem of graphene silicon Schottky junction, such as difficulty in providing high responsivity and high detectivity due to the dark current, has never been completely resolved. The conventional graphene silicon Schottky junction is being engineered by constructing a graphene gadolinium iron garnet silicon hybrid construction. The hybrid architecture is divided into two parts, which is the upper layer is graphene and the lower layer is n-type silicon. And gadolinium iron garnet thin film acts as an interlayer to facilitate carrier transmission. The fabrication is compatible with the conventional semiconductor process, which shows promise for building wafer-scale photodetector arrays. Photoresponse characterization revealed that the graphene gadolinium iron garnet silicon photodetector shows high performance in the self-powered mode in terms of an I light to I dark ratio up to 8.2 times 10 power 6, a specific detectivity of 1.35 times 10 power of 13 joules, and a speed of 0.15 millisecond at 633 nanometer. This study proved that capacity of gadolinium iron garnet as an interlayer material and provides a new approach for high performance photodetectors. This is the flowchart of the fabrication process of the graphene gadolinium iron garnet silicon photodetector. Gadolinium iron garnet is deposited on an exposed silicon window via radio frequency magnetron sputtering technology. The graphene is at the top layer, while the silicon at the lower layer, Schottky junction form, and the gadolinium iron garnet facilitate carrier transmission. Next, the fabrication is slightly doped with n-type silicon wafer with 300 nanometer silicon oxide to load the top electrode. And then the process is proceed with the removing of natural oxide layer on the substrate backside using buffered oxide. Titanium arum of 20 nanometer or 80 nanometer bottom electrode immediately deposited by e-beam vapor deposition for the forming ohmic contact with silicon substrate. And then the square junction area defined with ultraviolet lithography on the front side. Silicon dioxide was etched away to expose the underlying silicon. Gadolinium iron garnet thin film was then deposited on the n-type silicon window, forming an interfacial layer. And then it followed by the transferring of CVD ground graphene film on the gadolinium iron garnet coated surface to build a graphene gadolinium iron garnet silicon Schottky junction. And finally, ultraviolet lithography and e-beam vapor technologies were used again to define and deposit the titanium arum 20 nanometer or 80 nanometer at the top of electrode. Figure 1 shows the cross-section of the proposed graphene gadolinium iron garnet silicon photodetector. This slide shows about the photoresponse mechanism after the insertion of the gadolinium iron garnet. The plot of the semi-logarithmic current voltage IV curve of the device from which the typical rectifying properties is observed. The ideality factor and reverse saturation current are extracted to be 3.1 and 6.5 times 10 power of negative 9 ampere for the graphene silicon photodetector and 2.0 and 7.2 times 10 power of negative 10 ampere for the graphene gadolinium iron garnet silicon photodetector. In addition, the Schottky barrier heights are calculated to be 0.81 electron volt and 0.87 electron volt. Taken together, these results suggest that the inserted of gadolinium iron garnet interlayer can suppress the reverse saturation current and increase the Schottky barrier height, making the junction closer to the ideal Schottky diode so that the ideality factor becomes lower. Due to the inevitable dangling bonds of graphene and the non-ideal surface of silicon, an actual graphene silicon Schottky junction usually has a high density of surface states, which results in large carrier recombination, as shown in figure 1c. The rectifying Schottky barrier and built-in electric field have been improved after inserting the gadolinium iron garnet. The homogeneous interlayer with fewer structural defects helps to facilitate the interface and reduce the density of surface states, thus decreasing the recombination current, as shown in figure 1d. Next, when the junction is irradiated, photo-generated carriers are produced and separated by the built-in electric field. The holes are injected into the valence band of graphene, while the electrons move into silicon, which subsequently leads to a photocurrent, as shown in figure 1e. The insertion of a gadolinium thin film, as shown in figure 1f, allows photo-generated hole tunneling to graphene, and the impact ionization effect during the tunneling process functions as photogain to increase the photocurrent. When a reverse bias voltage is applied externally, graphene opens up more accessible states for photoexcited holes, hence resulting in a larger photocurrent. Diagram 2a shows that at operating voltage of negative 2 volt, the dark current of the proposed device is measured to be 2.35 nanoampere, which is 54 times lower than that of the graphene silicon photodetector. Meanwhile, the photocurrent increased from 0.26 milliampere to 1.04 milliampere so that the light to dark current ratio is as high as 4.4 times 10 power of 5. Figure 2b shows that the responsivity of the improved photodetector is 0.90 ampere per watt. In addition, the impressive specific detectivity and noise equivalent power of the graphene gadolinium iron garnet SI photodetector are 5.25 times 10 power of 12 joules and 0.03 picowatt per hertz respectively. This slide shows the performance of graphene gadolinium iron garnet silicon Schottky photodetector. Figure 2c shows the rise of photocurrent as the intensity increased slightly from dark to 5.2 nanowatt per centimeter square. Figure 2d shows the stable operation capability in a wide range of light intensities. while figure 2e shows intensification of the current at each wavelength reveals a multi-band operation covering to ultraviolet to near infrared range. Values of detectivity and noise equivalent power at a negative 2-volt bias, which shows a peak sensitivity at approximately 890 nanometer as shown in figure 2f. Next, figure 2a shows that this novel photodetector exhibits the advantage of high specific detectivity and a large light to dark current ratio at 633 nanometer under zero bias. Figure 3b shows the response times defined as an increase in the photocurrent from 10% to 90% is observed to be 0.15 millisecond, while the recovery time defined analogously is 0.16 millisecond. Figure 3c shows the photocurrent and dark current are almost constant during 500 continuous operation cycles with a period of 10 seconds. Figure 3d shows that the device maintains proper detection ability after 1 month with a relatively small photocurrent decay of approximately 9% followed by another 3% after the second month, demonstrating better environmental and time stability than the previous solution-based interface. Next, this is the second journal, which is about ultrafast photodetector by integrating perovskite directly on silicon wafer. The executive summary. Response times for single crystal perovskite photoconductive devices are frequently too low. More significant research should focus on integrating perovskite on silicon to enable broad spectrum and high detection given the potential benefits of doing so. Researchers have been working continuously to enhance device performance in order to meet application requirements in order to build high-speed optoelectronic devices. For instance, a heterojunction photodetector based on CH3 NH3 PBBR3 with a peak responsiveness of up to 11.5 mA per watt was created via a two-step process. But the response time was constrained by the substantial number of defects. A better interface silicon wafer directly integrated with single crystal MAPB-BR3 via an optimized anti-solvent vapor-assisted crystallization (OAVC) technique. The photodetector based on MAPB-BR3 on the silicon substrate have been thoroughly investigated and it exhibits excellent photo response characteristics, including wide spectrum range from 405 to 1064 nanometer, detectivity up to 519 times 10 power of 10 joules at a bias voltage of 1 volt, and ultra-fast reaction time of up to 520 nanoseconds. The enhanced contact between the silicon and single crystal perovskite may be the cause of this remarkable performance. This is the flowchart of fabrication and characterization of the single crystal MAPPB R3 on a silicon substrate. The first step is the CH3, NH3Br, and PBBr2 powders were dissolved in DMF under active mixing to prepare the MAPB-BR3 solution. As clean and type-like, doping silicon substrate was placed into a small beaker fully filled with MAPB-BR3 DMF solution. The next step is the small beaker was placed in a weighing bottle together with 2 ml of CH2Cl2 solvent, and then the bottle was covered with the lid at room temperature. Next step, MAPB-BR3 single crystals were ground gradually on the silicon substrate along with the slow diffusion of anti-solvent CH2Cl2 vapor into the MAPB-BR3 solution. Next, the aurum electrodes of 50 nanometer were deposited onto the single crystal MAPB-Br3 through a shadow mask. Finally, the silver electrode utilized to form ohmic contact with silicon was deposited on the backside of the substrate. This slide shows the device schematic and photoelectric switch characteristics. Figure 4a shows the structure of silicon MAPB-Br3 aurum photodetector. 173 nanosecond photoresponse time under an excitation wavelength of 480 nanometers shorter than that of the reported single crystal perovskite of 327 nanoseconds shown in figure 4b. From the time response under a 30 kHz pulse at the wavelength of 505 nanometer, the rise time from 10 to 90% peak value and fall time from 90 to 10% peak value can be estimated to be 520 and 2435 nanoseconds respectively, which is shorter than those of most of the reported perovskite-based photodetectors and conventional devices measured by continuously light sources shown in figure 4c. Figure 4d shows the time domain response of the silicon MAPB-Br3 aurum device under the light power density of 100 microwatt per centimeter square at bias of negative 0.5, negative 1, and negative 1.5 volt. It shows that the device has excellent on and off characteristics. This slide shows the detection performance and mechanism of the silicon MAPB-Br3 aurum single crystal heterojunction devices. Plus the IV curve of the silicon MAPB-Br3 aurum photodetector under illumination of different wavelengths from 405 to 1064 nanometer with light power density of 225 microwatt per centimeter square is shown in figure 5a. Photocurrents with a strong dependence on light intensity as a function of light intensity and wavelength from 405 to 1064 nanometer at the bias of negative 1 volt shown in figure 5b. And figure 5c shown that the detectable wavelength range is much wider than that of pure perovskite devices with the wavelength range below 700 nanometer. Photocurrents as a function of wavelength under light illumination with the intensities of 103 and 225 microwatt per centimeter square at bias of negative 1 volt. This slide shows the device characteristics and performance comparison. Figure 6a shows the response time of perovskite that is basically on the order of microseconds suffer from a narrow detectable wavelength range due to the inherent optical bandgap of perovskite. The shorter response time can be achieved by decreasing the device area and thickness. It's noted that the response time of this photodetector is comparable to that of representative high-performance solution process hybrid perovskite photodetectors and commercial germanium-based photodetectors. Figure 6b shows that optoelectronic devices with similar device structure are also listed for comparison. By inducing organic functional groups at the interface of silicon and perovskite, the response time is 255 microseconds, which is much slower than that of our detector. Meanwhile, due to the synergistic effect in silicon and perovskite, our photodetector's detectable wavelength range from 405 to 1064 nanometer is wider than that of normal devices. This is the schematic of the imaging process using the prepared silicon MAPB-Br3 aurum heterojunction devices. A smaller silicon MAPB-Br3 and aurum photodetector with an area of 1.9 times 10 1.9 mm square was prepared as a single pixel for imaging purpose. In this work, the gray imaging capability of the silicon perovskite photodetector was investigated via self-assembly imaging system, which consists of micro displacement and projection equipment. The operating process can be explained as two steps. First, the grayscale image were received and converted into current signal by continuously moving to the detector of an XY stage. Second, the current signals were converted inversely to image information. Figure 7b shows the optical pattern of 1, 2, 3 is presented at the bottom by scanning the device, which shows that the device has a good resolution compared to that of the original projection image at the top. Figure 7c shows the obtained phase image by scanning silicon MAPB BR3 ARM devices. Grayscale phase image shows that the device has excellent imaging capability. Next, this is the geometry, which is light intensity dependent photoresponse time of organic photodetectors and its molecular origin. The executive summary. Small molecules and conjuncted polymers, among other organic semiconductors, constitute a new class of appealing photoactive materials for photosensing in diverse imaging applications. Despite many success, OPD's principal drawback in comparison to their crystalline inorganic counterparts continues to be their very long photoresponse times. Here, we clarify how donor molecular structure affects trap state generation in core of evaporated carbon-60 bands and how it affects the light intensity dependent photoresponse duration of bulk heterojunction organic photodetectors made using these bands. In core sublime bulk heterojunction organic photodetectors, the carbon-60 acceptor and two small molecules donors NPSA and MPTA respectively for their chemical structures are employed. Under relatively intense light irradiation, which is 1 sundown to 0.5 milliwatt per centimeter square, a planar donor MPTA produces a faster OPD response than a twisted donor NPSA. The molecular beginning of trap states in bulk heterojunction organic photodetectors and how molecular design requirements can vary for high and low lights device operation are both crucial insights provided by this research. This is the flowchart of fabrication of devices and thin film. The first step is all organic semiconductor materials were purified via sublimation under high vacuum, lower than 10 power of 6 torr prior to use. Then the thin films were fabricated via thermal evaporation under high vacuum, which is lower than 10 power of -7 torr at a rate of 0.35 ampere per second on dry glass or quartz substrates. Then the OPDs were fabricated on ITO coated glass substrate. The next step is all organic film layers were thermally evaporated under high vacuum, which is lower than 10 power of -7 torr. Next, ITO electrodes were evaporated by magnetron sputter before the devices were finally encapsulated with glass. Next, thermal annealing post-fabrication of thin films was performed at 160 degrees Celsius over a hot plate for 3 hours. Finally, they are thanks to natural cooling to room temperature. Diagram 8 shows molecular structure of NPSA and MPTA donors with their donor and acceptor units indicated. The spatial conformation of donor molecules is illustrated based on the DFT optimized geometries shown as side views. This diagram shows OPD device of characteristics at high light intensity. Figure 8a shows light of photocurrent transient at the light intensity range of 0.6 until 2.2 milliwatt per centimeter squared, illumination at 0 volt. The device was illuminated for 100 milliseconds before switching off the light. The background current level is higher than the dark current of the device due to the sensitivity limitation of the detector circuit. Figure 8b shows the effective charge carrier mobilities as a function of charge carrier densities analyzed by charge extraction at 0 volt at the light intensity range of 0.5 until 100 milliwatt per centimeter square. Figure 8c shows normalized plots of the charge carriers density at open circuit versus open circuit voltage determined from integration of charge extraction transients as a function of light irradiation intensity. This slide shows the low light illumination photocurrent transients. Figure 9a shows the bandwidth of frequency response at photocurrent density of 2.7 microampere per centimeter square with the light intensity of 0.024 milliwatt per centimeter square at 0 volt. Figure 9b shows the NPSA carbon-60 device photocurrent transient measured by charge extraction CE at 0 volt. Next, figure 9c shows MPTA carbon-60 device photocurrent transient measured by CE at 0 volt. And diagram 9D shows a comparison of current transient measured at 0.5 milliwatt per centimeter square. The photocurrent transients of MPTA carbon-60 is fitted with a double exponential decay function, green dashed line. This slide shows the energetic analysis of NPSA carbon-60 and MPTA carbon-60 bands. Figure 10a shows the photoemission spectra of net and blended donors measured by APS with the linear fix for the location of emission age attribution to highest occupied molecular orbital. The inset shows the density of tail states extracted from the integrated area below the highest occupied molecular orbital and set indicative of shallow trap density with error bars as standard deviation across multiple measurements. Figure 10b shows distribution of deep and shallow trap states. MPTA carbon-60 has a narrower shallow trap distribution and the presence of a deeper trap dose. The trap states are filled by photogenerated holes from low energy states to high energy states gradually with the increase of light intensity. In low light, hole extraction from deep states of MPTA carbon-60 is harder than the extraction from shallow states due to the higher energy barrier, leading to hole trapping in deep states. This is the overall comparison. Figure 11a shows at operating voltage of negative 2 volt, the dark current of the proposed device is measured to be 2.35 nanoampere, which is 54 times lower than that of the graphene silicon photodetector. Meanwhile, the photocurrent increased from 0.26 milliampere to 1.04 milliampere, so that the light to dark current ratio is as high as 4.4 times 10 power 5. Figure 11b shows that light on and off frequency response characteristics from the times response under a 30 kHz pulse at the wavelength of 405 nanometer, the rise time from 10 to 90% peak value and fall time from 90 to 10% peak value can be estimated to be 520 and 2000 435 nanoseconds respectively, which is shorter than those of the most of the reported perovskite-based photodetectors and conventional devices measured by continuous light sources. While figure 11c shows the faster charge extraction transients were observed for MPTA carbon-60 devices at the light intensity ranging from 0.6 to 2.2 milliwatt per centimeter square, consistent with the wider frequency response bandwidth of the MPTA carbon-60 organic photodetectors. Overall conclusion for the first journal. As a conclusion, the fascinating characteristics of gadolinium iron garnet plays an important role in modifying the graphene silicon Schottky junction that can produce stronger Schottky barrier and lower surface states resulting from the gadolinium iron garnet interlayer can work as a high performance interlayer photo detection and may hold dominance in next generation light sensing application. For second journal, Direct integration of single crystal perovskite on silicon with an improved interface resulted in the fabrication of high-performance silicon MAPB-BR3 heterojunction photodetector. The photodetector has the widest spectral range from 405 to 1064 nanometer and a detectivity of up to 5.9 times 10 power of 10 joules at a bias voltage of 1 volt. It also has an ultra-short rise time of 520 nanosecond under light illumination at 405 nanometer. The device's imaging capability is demonstrated by grayscale phase image. These findings imply that this optimized AVC direct growth method and device preparation technology will enable future broadband spectrum and high-speed imaging for optoelectronic devices. The conclusion for the third journal: the control of the density of shallow trap states achieved in MPTA by its highly planar molecular conformation is a major factor for the fast charge transport and photoresponse time found in MPTA carbon-60 devices under conventional illumination circumstances of high light intensity. This extremely planar molecular shape, however, causes substantial intermolecular coupling between MPTA molecules, resulting in a low bandgap state. This coupling is greatly disrupted in blends with carbon-60, resulting in a hormone level shift of several hundred millielectronvolt for most MPTA molecules. This is a summary for one preferred journal. The first journal is chosen based on this summary. This study demonstrates that a thin layer gadolinium iron garnet film can serve as an interlayer of graphene silicon Schottky junction photodetector with remarkably improved performance owing to the effective increase in the Schottky barrier height and passivation of the contact surface. The photoresponse measurement at a negative 2-volt bias show that the dark current of the photodetector decreased by 54 times, while the photocurrent increased slightly. More importantly, this novel structure exhibits high performance in a self-powered mode in terms of an light current to dark current ratio up to 8.2 times 10 power of 6 and a specific detectivity of 1.35 times 10 power of 13 joules, demonstrating remarkable advantage in weak light detection. Further practicability consideration reveal a broadband absorption spectrum covering ultraviolet to near-infrared, a near-linear response with a wide range of light intensities, and a speed of 0.15 milliseconds. The device also exhibits a stable response for 500 counts, continuous on-off cycles, and long-term environmental stability after several months. The intrinsic mechanism after inserting the interfacial layer has been explored through thermionic emissions theory and the energy bandgap structure. The decreased reverse saturation current and the increased Schottky barrier height play a dominant role in this development, which suppress the thermally generated charges and facilitates the transport of photogenerated carriers. These findings reveal the good prospects of gadolinium iron garnet film as an interface engineering material and provide a new approach for high-performance gadolinium graphene silicon Schottky photodetectors. That's all from me. Thank you.